Welcome to the Dash-8 Q400 Systems Course Hydraulics module. In this module, we will introduce the hydraulic system, talk about the various systems served by the hydraulic system, and then discuss the number 1 and number 2 systems in depth, including discussions about the reservoirs and shutoff valves, engine-driven pumps, isolation and priority valves, the brake accumulator, and the standby Hyd Pump and the PTU. Afterwards, we'll discuss the number 3 hydraulic system and the alternate gear extension system, before talking about the hydraulic system indications in the flight deck. We'll end with a discussion of the myths and facts regarding hydraulic fluid transfer between the two systems. And as always, we'll end with limitations and normal and abnormal procedures of the hydraulic system. The hydraulic system in the Dash-8 Q400 provides power to many key systems on the aircraft. The hydraulic system runs at a high pressure, 3,000 psi, and is able to provide a large amount of force to several high-demand items on the Q400, including the elevators, rudder, spoilers, flaps, landing gear extension, nose wheel steering, and brakes. There are a total of 4 separate hydraulic systems on the Q400. The number 1 and number 2 systems are the primary systems. They are very similar in design to each other and power most of the systems listed above, with redundancy included for critical systems like the flight controls. The number 3 system is an emergency system that provides power only to the elevators when systems 1 and 2 fail. And a 4th system is included that provides a means for manual extension of the landing gear. Each hydraulic system in the Dash-8 feeds a separate set of systems around the aircraft. Here is a memory tool to help you remember which system feeds which systems. FARE EP and Loaner E. FARE EP for the number 1 system stands for flaps, anti-skid brakes, inboard spoilers, rudder, elevator, and PTU. Loaner E for the number 2 system stands for landing gear, outboard spoilers, nose gear steering, emergency brakes, rudder, and elevator. Note that both primary systems control the rudder and elevators, and in fact System 3 also actuates the elevators as well in an emergency. In these cases, the systems do not connect in any way. The systems simply drive different actuators on the same surface. For example, the number 1 system drives the lower rudder actuator, while the number 2 system drives the upper rudder actuator. To help you remember this, think about number 1 being the lower number. For the elevators, the number 1 system controls the outboard actuators, the number 2 system controls the middle actuators, and the number 3 system controls the inboard actuator on each elevator. The number 1 and number 2 hydraulic systems on the Q400 are fairly similar, though with a few distinct differences. Let's explore the different components of these two systems in the order that fluid will flow through the system. Each system is powered primarily by the same number engine and served by a reservoir located in the landing gear bay behind the same engine. This allows the reservoir to be visually inspected and serviced through the landing gear bay. During normal operation, pressure from the hydraulic system itself drives a piston in the reservoir that helps to pressurize the fluid within the reservoir and forces the fluid out through the reservoir exit and into the pump. This pressure exerted on the fluid in the reservoir eliminates the possibility of the hydraulic pumps cavitating as long as there is still fluid in the system. Each reservoir incorporates a temperature and fluid level sensor to indicate how much fluid is in the system. Quantity is displayed on the MFD as will be shown later, and a high temperature on the sensor will trigger the number 1 or number 2 hide fluid hot caution lights. After exiting the reservoir, the hydraulic fluid passes through a firewall shutoff valve. This valve is normally open, but will close under any of the following conditions: if the respective engine fire handle is pulled, if the hydraulic fluid quantity in the respective system is low, or if a hydraulic fluid overheat has been detected. Hydraulic fluids are flammable and can ignite at the high temperatures in the engine compartment. Stopping their flow is important to extinguishing or helping prevent an engine compartment fire. The position of the hydraulic firewall shutoff valve for each system is indicated on the overhead fire protection panel. A green light illuminates for each engine hydraulic system if the corresponding valve is fully open, while a white light illuminates if the corresponding valve is fully closed. The primary source of hydraulic pressure for the number 1 and number 2 hydraulic systems in the Dash-8 is the engine-driven pump, or EDP, mounted on the respective engine's propeller gearbox. The EDPs provide sufficient hydraulic pressure and flow rate for all hydraulic services on the respective system, and are regulated to maintain an ideal pressure of 3,000 psi in each hydraulic system at all times that the engine is running. A heat exchanger is also located in each fuel tank collector bay to cool hot hydraulic fluid. Each EDP has a case drain where excess fluid exits the pump without entering the pressurized part of the hydraulic system. A thermal bypass valve diverts some of this fluid from the case drain into the heat exchanger to maintain the hydraulic fluid at a normal operating temperature. The higher the fluid temperature, the more of it runs through the heat exchanger to help prevent the fluid from overheating and possibly auto-igniting. Pressurized fluid leaving the EDP also passes a pressure sensor, which is connected to the number 1 or number 2 Hyd Pump caution light, and these illuminate when the pressure in the given system falls below a certain value, indicating that the pump is offline, either because the engine is off or the pump has failed. After this pressure sensor, the fluid passes through a check valve before being routed to the various services. This check valve is necessary as there is a backup source of pressure for each hydraulic system. After passing this check valve, the hydraulic fluid is distributed to the various systems throughout the aircraft. After the pressurized fluid is used by the system, the fluid is collected and routed back to the hydraulic system reservoir, mainly through residual pressure after passing through the service, so that the fluid can be reused. Each of the main hydraulic systems contains an isolation valve, which is normally open. If system fluid quantity, as measured in the reservoir, falls below a certain value, then the isolation valve will automatically close within the corresponding system. This isolation valve then stops hydraulic fluid from flowing to certain services, helping to feed certain critical services and keep them functioning. The critical services that are not cut off by the isolation valve are basically the primary flight controls, including the flaps, the PTU, rudder, and elevators in System 1, and only the rudder and elevators in System 2. Systems that will go offline include the landing gear, spoilers, brakes, and nose steering, depending on whether the System 1 or 2 isolation valve is closed. When either isolation valve closes, it also illuminates the corresponding number 1 or number 2 Hyd ISO valve caution light. There is a second similar valve in the number 1 system only, called the priority valve. It has a similar function to ensure sufficient hydraulic power remains to serve the rudder and elevator at all times. However, this valve relies on pressure, not quantity. Should the pressure in the number 1 system fall below 2100 psi, this triggers the priority valve to close to ensure that rudder and elevator control are not degraded during high hydraulic demand periods. Usually the primary source of this high hydraulic demand is the flaps. As the pressure is restored in the system, the valve will open again and the flaps will continue to move until the pressure drops again. The flaps will eventually reach their intended position, but at no time will the rudder and elevator control be degraded during the flap deployment. One other difference between Systems 1 and 2 is the hydraulic accumulator for the emergency parking brake system, which is only on System number 2. The emergency parking brake needs to be available even when the engines are not running. For this reason, an accumulator stores pressure from the number 2 hydraulic system and will maintain 3,000 psi even when the number 2 system is depressurized. Essentially, the accumulator is a cylinder and piston with nitrogen gas sealed on the far side of the piston. At 3,000 psi in the hydraulic system, this gas is then compressed and stores energy much like a spring. When the pressure in the hydraulic system falls, the gas will expand again and will push some of the hydraulic fluid back out of the accumulator, helping to maintain some pressure in the emergency parking brake system, though there is a limit to how long this will work for. When fully charged to 3,000 psi, this accumulator will normally allow about 6 operations of the emergency parking brake before pressure in the accumulator is fully depleted. This is usually enough for most ground operations, and will also help if there is a complete failure of the number 2 hydraulic system, as 6 emergency or parking brake applications are available to help stop the airplane at the gate or even on the runway if the anti-skid brakes are also unavailable. The accumulator pressure is displayed on the MFD permanent system area and will be discussed later. In case of excessive brake applications during ground operations, such as towing to or from the hangar, there is a way to repressurize the accumulator without the use of the EDPs. Within the right-hand landing gear bay, near the hydraulic reservoir, there is a hand-operated pump. This pump requires a landing gear alternate extension handle from the flight deck, and when inserted in this pump, one can use it to repressurize the parking brake accumulator. Note that to access this hand pump, the landing gear doors must be opened. This can be accomplished by pulling the alternate landing gear extension handle in the flight deck. To aid with pressurizing the accumulator from the hand pump, there is a small pressure indicator located behind a small window on the fuselage just below the right wing root. The gauge is quite small and can be a bit hard to see, but it is easier than walking back and forth to the flight deck to check your progress in recharging the accumulator. Each of the main hydraulic systems, number 1 and number 2, has a backup source of hydraulic power. For the number 1 system, this is an electric hydraulic pump installed in the number 1 engine nacelle and known as the standby hydraulic pump. It provides a backup source of pressure to the number 1 system, though it does not provide as much flow as the EDP, so systems, especially the flaps, will run slower. The standby Hyd Pump is powered by AC power from the right AC bus. This provides a level of hydraulic redundancy. If the left engine fails and the number 1 EDP stops working, the standby hydraulic pump can provide hydraulic pressure to the number 1 system using AC power from the still running right engine. The standby hydraulic pump can be activated manually or automatically. A switch on the right side of the main panel allows the pump to be manually turned on. This is normally done for takeoff and landing to prevent loss of hydraulic services should an engine failure occur during either of these critical events. The standby pump is normally turned off in flight to save wear on the pump. Whenever the pump is switched on and is actually turning, the switch light illuminates with an on indication. The standby pump is also automatically activated if the left engine fails or the number 1 reservoir is not empty, the parking brake is off, and the flaps are greater than 0 and AC power is available. For this second condition, these conditions are normally met anytime the aircraft is taxiing, taking off, or landing. This automated system ensures sufficient hydraulic pressure is available during critical flight times. However, relying on the automated system causes more wear and tear on the pump and the related wiring, as the pump will cycle off and on each time the parking brake is set and released during taxi. This is why the manual switch is used to force the pump on for the entire takeoff, landing, and taxiing period. The Power Transfer Unit, or PTU, is the backup source of pressure for the number 2 hydraulic system. The PTU consists of a hydraulic motor and a hydraulic pump. The motor is very similar to a hydraulic pump, but acts in reverse. High-pressure fluid flowing through the motor in the number 1 system causes the motor to turn, changing this hydraulic pressure into rotational energy. This motor is connected by a shaft to a hydraulic pump in system number 2, which provides hydraulic pressure to system 2 whenever the PTU is turning. A valve in the input line from the number 1 system is what controls operation of the PTU. Anytime the PTU is activated, this valve opens, which allows pressure from the number 1 system to turn the PTU. It is very important to note that there is no direct connection between the hydraulic lines in the PTU. It is not possible for fluid to transfer from system 1 to system 2 or the other way through the PTU. Only power is transferred from one system to the other through the motor, the pump, and the shaft that connects the two. The PTU is activated using very similar logic to the standby electric pump. It can be manually activated at any time using the switch on the panel and will automatically operate when the following is true. The number 2 reservoir is not empty, the parking brake is off, the flaps are greater than 0, and the number 1 EDP is at greater than 2400 psi. Again, note that these conditions basically occur during taxi, takeoff, and landing. And again, it is preferable to activate the PTU manually during these times to prevent the valve from cycling repeatedly if the parking brake is turned on and off during taxiing. One special note about automatic operation of the PTU. If the number 2 hydraulic system does not reach its minimum pressure within 30 seconds of the PTU automatically operating, the PTU is deactivated and locked out. The PTU cannot be started again, manually or automatically, for the remainder of the flight until maintenance action occurs. This protection does not occur during manual operation of the PTU. The number 3 hydraulic system in the Dash 8 is very different from the first two systems. The number 3 system is very simple and serves one simple purpose: to provide backup control of the elevators in case of severe catastrophic failure scenarios, including loss of one or both main hydraulic systems, or even a dual engine failure. Again, the number 3 system is very simple. It consists of a reservoir, a single electric pump, an accumulator, an isolation valve, and the elevator actuators. The reservoir is similar to the number 1 and number 2 system reservoirs, complete with a pressurization piston, powered again by the number 3 system itself. This reservoir simply has a much smaller capacity than the other reservoirs because it is providing much less service. The pump for the number 3 system, called the DC motor pump, or DCMP for short, is powered by, surprise surprise, DC electric power directly from the standby battery. Since the DCMP does not rely on AC power, unlike the standby Hyd Pump, it can be powered even when there are no engines running to provide a source of AC power. The DCMP is located in the tail of the Q400 along with the number 3 system reservoir. This helps to keep the hydraulic lines short, as they only need to flow from the reservoir to the pump to the elevators and back again. The DC pump works in conjunction with a hydraulic accumulator similar to the one in the number 2 system for the parking brake. It helps to maintain a relatively constant pressure in the number 3 system without requiring the pump to run all the time. This avoids excess current draw and wear on the DC pump. Pressure sensors in the hydraulic accumulator in the number 3 system sense when pressure falls below 2600 psi and then activates the pump until the pressure rises again to 3250 psi. The DCMP is then shut off and the accumulator maintains pressure in the system. However, the pressure will eventually fall in the system, especially if the service is being used, and the pump will reactivate to restore pressure in the system when necessary. A second sensor in the accumulator triggers when the pressure in the number 3 system falls below 900 psi, and this triggers the number 3 Hyd Pump caution light. This light can also be triggered if the DCMP runs for more than 60 seconds consecutively while on the ground. Either of these scenarios indicates a potential problem with the DCMP or the number 3 hydraulic system. After the DCMP and the accumulator, there is a valve called the isolation valve, which prevents hydraulic pressure from the number 3 system from reaching the elevator actuator. This isolation valve is closed during normal operations, and the number 3 system is prevented from actuating the elevators. In this way, the number 3 system is always in an active standby mode. The system always has pressure available within the system and is able to quickly begin activating the elevators at any time by simply opening the isolation valve. The isolation valve is selected open either manually using the Hyd ISO valve switch on the main panel, or automatically if either the number 1 or number 2 hydraulic system is not operating properly, or if a dual engine failure occurs. It should be noted that if, at any time, all 3 hydraulic systems are actuating the elevators, the elevator press caution light will illuminate. The fourth hydraulic system in the Dash 8 Q400 is the simplest system yet. It is the alternate landing gear extension system. This system consists of a very small reservoir, a hand pump, and a selector valve. The reservoir is located in the nose of the aircraft and is the smallest reservoir of any hydraulic system at only 1.2 liters. The selector valve is used to release pressure in the alternate system. It is normally open so that fluid can flow freely in and out of the alternate landing gear actuators and does not impede the normal operation of the landing gear. When the landing gear alternate extension door, which is on the floor of the flight deck, is opened, the selector valve is closed, locking in any pressure that exists into the actuators. With the landing gear alternate extension door open, the alternate extension handle can now be inserted into the hand pump located in the floor of the flight deck. When this is done, hydraulic fluid can be manually pumped through the alternate extension system into the alternate actuators for the landing gear by pumping the handle back and forth. This helps to force the landing gear into the fully extended and locked position if it is not already free-falled all the way to the down and lock position. There is more information about the alternate gear extension in the landing gear module. There are a few locations on the flight deck where information about the hydraulic system is presented. Firstly, there are the 3 switch lights on the main panel for the hydraulic system. The standby high press switch light controls the number 1 system standby pump and illuminates on anytime the button has been pressed to activate the pump. Automatic operation does not illuminate this switch light. The PTU control switch, when pressed, allows pressure from the number 1 system to enter the motor side of the PTU. There are 3 light segments in this switch. The on light segment indicates the switch has been pressed to open the valve. The green hashed bar indicates that there is pressure in the output line from the PTU pump in the number 2 system, indicating that the PTU is working. A fail light illuminates if the PTU does not produce pressure within 5 seconds of being activated. The Hyd number 3 ISO valve switch, when pressed, opens the isolation valve in the number 3 system, activating the inner elevator actuators. The open light indicates the valve has opened successfully and the number 3 system should be powering the elevators. There is also an indication of hydraulic system status on MFD2 in the Permanent System Area, or PSA. This area will remain displayed as long as both MFDs are working and in MFD mode. This area displays the following values: parking brake accumulator pressure, standby Hyd Pump output pressure, and system pressure in the number 1, number 2, and number 3 systems. For each pressure reading, each mark on the scale indicates 1000 psi. Hint, each pressure should normally be at 3000 psi, the third mark if the system is operating normally. The final indication on this permanent system area are the hydraulic fluid quantities in reservoirs 1, 2, and 3. In these cases, the scales indicate 25% increments. If the indicator is at the top of the 4-mark scale, the reservoir is 100% full. If there is a failure of either MFD, or either MFD is not operating in MFD mode, the remaining MFD will display the same hydraulic system indications, but using a digital readout instead of an analog measurement as shown here. All the values are included in the digital view, but shown in the smaller format to ensure there is also room to show both sets of system indications, hydraulics and flight controls, on a single display. There is one misunderstood and often abused quirk of the hydraulic system in the Q400. Many pilots and instructors will say that you cannot transfer fluid between the number 1 and 2 systems, and usually when they're speaking about the PTU, they are correct. However, this is not completely true. There is one place where the 2 systems meet and the aircraft can transfer fluid between the 2 systems, and that is at the brakes. The aircraft brakes on the Q400 can be operated by the anti-skid system through the rudder pedals, or through the lever-controlled parking brake. The anti-skid uses number 1 hydraulic pressure, while the parking brake uses number 2 hydraulic pressure. However, both systems actually drive the same brake calipers. A shuttle valve moves back and forth to allow whichever service is sending a higher pressure signal to activate the brakes. However, this can also allow fluid trapped in the brakes to be transferred from one system to another. The most common scenario you'll see in the Dash 8 is that pilots will press the rudder pedals, stop the aircraft, and then set the parking brake. Because the pedals were being held first, they forced fluid into the calipers. However, many Dash 8 pilots release the parking brake without holding the rudder pedals down. The fluid in the calipers then exits the calipers into the parking brake system. Each time, only a small amount of fluid is transferred, but if pilots do this a dozen times a day, after a few days, the number 2 system will eventually reach full and overflow, while the number 1 system has lost fluid and needs to be replenished. It is possible to undo this by applying the reverse process. If a pilot notes the number 2 reservoir is at or very close to 100%, while number 1 is much lower, fluid can be transferred back by stopping the airplane and holding it stationary by disking the prop. Then, apply the parking brake, press the rudder pedals, release the parking brake, and release the rudder pedals. This process will need to be repeated many times to undo the fluid level imbalance, as each time only a small amount of fluid is transferred. But it is possible and, with practice, can be done quite quickly by an experienced pilot. Strictly speaking, there are no operational limitations associated with the hydraulic system on the Dash 8. However, there are a few dispatch requirements you should be aware of. Prior to dispatch, the minimum level of fluid in the number 1 and number 2 hydraulic system reservoirs is 40%, while for the number 3 system it is 45%. There is also a minimum parking brake pressure that must be observed prior to starting engines. If the number 1 engine will be started first, the minimum accumulator pressure required is 1000 psi. If the number 2 system will be started first, the minimum pressure for start is 500 psi in the parking brake accumulator. Most of the functions of the hydraulic system are automatic on the Dash 8. The number 3 system will pressurize as soon as DC power is turned on, and the number 1 and number 2 systems will normally pressurize when their respective engine is started. The only normal procedure that must be manually accomplished is manually activating the standby Hyd Pump and PTU for takeoff and landing. This ensures hydraulic pressure remains available in case of any engine failure during takeoff or landing, and also helps ensure sufficient extra power in the hydraulic system for high-draw services such as flaps and landing gear operation. For takeoff, these are normally turned on after starting the engines, or after the first engine start anyways for single-engine taxi, and turned off in the after takeoff checklist. For landing, these are normally turned on just prior to selecting the flaps greater than 0. After landing, they are deactivated once the parking brake is set at the arrival gate. If single-engine taxi is to be used, it is imperative that the standby pump be activated manually prior to taxiing on a single engine, whether prior to taxi for taxi out, or prior to shutting down engine 1 for taxi in. The number 1 system supplies the anti-skid brakes. If the airplane is taxied with engine number 1 off and the standby Hyd Pump off, there will be no pressure in the number 1 system and the anti-skid brakes will not work. If this happens, or if the number 1 system loses pressure for any reason during taxi, use the parking brake, carefully, to slow the aircraft. The hydraulic system on the Q400 is very important as it powers a number of different subsystems within the aircraft. There are a number of different abnormal procedures depending on the different failure modes of the hydraulic system. As always, follow the checklist. We'll start with the more benign failures and move to the most critical. With the hydraulic systems on the Dash 8, certain failure modes will cause multiple caution lights to illuminate. The easiest way to try to diagnose which failure you are having is to examine the hydraulic indications in the permanent system area. Most failures come down to either a loss of pressure or fluid, or both. By identifying which event is happening in the PSA, you can help to identify which checklist is most appropriate. If the number 1 or number 2 hide fluid hot caution lights come on, there is not much to do. Cooling of the hydraulic system is fully automated and cannot be changed by the pilot. The checklist just advises to monitor the hydraulic system closely. However, hot hydraulic fluids may indicate there could be future problems with the system. If the number 1 standby Hyd Pump hot caution light illuminates, the checklist is again quite simple. If the flaps are already up, turn off the pump and continue on. Hopefully the pump will cool itself once it is deactivated. If the pump does cool and the light goes off, it can be used again. If the PTU fail light segment illuminates, the PTU failure checklist states to deselect the PTU and not reselect it again. The PTU will be unavailable for the remainder of the flight. Once failed, it can only be reset by maintenance action. The number 3 Hyd Pump caution light indicates a problem with the number 3 Hyd Pump generating pressure. Once again, there is nothing the crew can do for this failure except to complete the flight and call maintenance. Fortunately, the number 3 system is only a backup system, so as long as the number 1 and number 2 hydraulic systems continue to operate normally, the aircraft will operate normally. The number 1 engine Hyd Pump and number 2 engine Hyd Pump caution lights have very similar checklists. In both cases, you have lost the primary source of hydraulic pressure for the respective system, so the respective backup system, either the standby Hyd Pump or the PTU, must be activated to attempt to restore pressure to the system. One additional consideration for the number 1 system: the standby Hyd Pump provides less fluid flow than the EDP. This will have a pronounced effect on the flaps, which will deploy at a slower speed than normal. Be sure to anticipate this when configuring for landing. Next are the 1 and 2 hydraulic isovalve caution lights. These lights illuminate when the system detects a low level in the respective system's hydraulic reservoir and the isolation valve has already automatically closed. If this happens in the number 2 system, the PTU must be isolated to ensure it does not activate automatically or manually and use up additional fluid in the number 2 system. In either case, the flight controls continue to function. However, there are a number of subsystems which are lost when the isolation valve closes. That include, depending on the system, spoilers, brakes, and nose wheel steering. While not having an effect in the air, all of these will have an impact on the landing process. Consult the checklist carefully and be sure to select a long runway for landing. The required landing distance will almost double in these scenarios. Now we get to the big failures, the number 1 or the number 2 hydraulic system failure, also known as the loss of all fluid from the respective system. You have 4 different indications when this happens, and seeing all 4 of these confirms that you have the correct checklist. For example, for the number 1 system, you will see the number 1 Hyd Pump caution light, the number 1 Hyd ISO valve caution light, the number 1 Hyd valve will show closed on the fire protection panel, and the hydraulic system quantity indication is at, or at least very close, to 0. The checklists for these 2 systems are somewhat different, owing to the different designs of each system and the services lost with each system, though the checklists do follow a similar pattern. First, regardless of which checklist you use, the number 3 Hyd ISO valve should be opened to ensure the elevators continue operating normally. Next, the backup hydraulic pressure source must also be turned off, either the standby Hyd Pump or the PTU. And in case of the PTU, the circuit breaker must also be pulled to absolutely prevent automatic PTU operation, as well as manually selecting the PTU off. In the case of number 2 failure, the standby Hyd Pump is also activated to ensure the number 1 system is unlikely to lose pressure at any time. Lost services between the 2 systems vary, but will include some spoilers and some brakes. For the number 1, flaps are also lost, while for the number 2, landing gear extension as well as nose wheel steering will be lost. In either case, landing distance is greatly increased over normal landing, and selecting a long runway is a must. In the worst case scenario, if the number 1 system fails with flaps at either 5 or 0, the aircraft may require up to 2.65 times the normal landing distance. And now finally, the worst case scenario for the hydraulic system in the Dash 8 is a loss of both the number 1 and the number 2 hydraulic systems. While extremely unlikely, it is not completely impossible should aircraft damage occur in one of the areas common to both systems, such as brakes, spoilers, elevator, or rudder. If both systems number 1 and number 2 are lost, the only hydraulic service remaining on the aircraft is the elevators through the number 3 Hyd system and the associated actuators. All other hydraulic services on the aircraft are lost. The aircraft must be reverted to manual control, no autopilot, and must remain at a slower speed, 200 knots max, to ensure controllability and avoid potentially over-controlling and overstressing the aircraft. Roll control will also have reduced effectiveness without the roll spoilers, and the rudder will be completely unavailable. The only means of yaw control for the aircraft will be the use of asymmetric power if needed. Again, a long runway will be required due to the loss of normal braking and spoilers, as well as nose wheel steering. The flaps will also be stuck in their last position, which will also likely add to the landing distance required. Steering on the runway during landing will be especially difficult, as both nose wheel steering and differential braking will be unavailable. Only asymmetric power can maintain directional control on the runway, and this asymmetric use of power will also likely increase the landing distance even further, so selecting a long runway with minimal crosswind will be a top priority during this unlikely but not impossible scenario. We will now conduct a brief review. I suggest you prepare to pause the video as each question is displayed and attempt to answer it yourself before the correct answer is revealed. Let's begin.
This concludes the current module. I hope you found this information useful. Please ask any questions you may have in the comments section below. And please subscribe to the channel to be alerted when more modules are complete. Thank you for watching.